Good evening, everyone. Hope I am audible and you are able to see my screen. So we will wait for a couple of more minutes and we will start maybe by 6:02 or 6:03. Okay. So today mostly we will discuss some questions related with signals and systems topic. The first one you can see it's a question related with sampling theorem. Okay, and there will be a few questions related with digital filters and yeah, one question is related with fundamentals of like signals. Okay, so anyway, we will wait for a couple of more minutes. 6:02 or 6:03 will start. Okay, so let us start. Before that, whoever was there for the last class, for them, I will introduce myself again. I am Krishnan. I'm currently doing PhD at the Indian Institute of Science, Bangalore. Okay, so I will be handling this session Tuesday 6 to 7, maybe till the end of January or something. So I think the dates of GATE exam is already out. It's in the first week of January, in the first week of February. I think it's on February 5th, if I remember correctly. EC exam in the afternoon session. Okay, so yeah, this is the second session in phase two of this NPTEL GATE mentoring session. So the first one lasted for 12 weeks from September to November end. Okay, the November mid. So this is the second phase, second session. So mostly I will be doing questions related with communication systems, signals and systems, and some engineering mathematics, maybe related with linear algebra or probability theory. Okay, if you are having some specific questions, you can raise or you can uh, send the question numbers. I will be doing some questions related with the previous GATE exams. Okay, all the questions are more or less from the previous GATE EC exams. So this is a question from 2014. So in 2014, there were more than one sessions. This is a question from session 3, okay, of 2014 GATE EC paper. And you can see this is a question related with sampling of continuous signals. So the question is as follows. Let x of t equal to cos 10 pi t plus cos 30 pi t be sampled at 20 Hz and reconstructed using an ideal low pass filter with cutoff frequency of 20 Hz. The frequency or frequencies present in the reconstructed signal is or are. Okay, this is a multiple choice question and you can see 4 options. So before getting into the solution of the problem, we will discuss some facts or some theory behind it, maybe related with sampling of continuous signals. Okay, I will not do it in a proper mathematical way. I will try to like make you understand this in a more intuitive way, maybe pictorially. Okay, so let's forget about the question for the time being and let us see what is sampling. Okay, so so all of you may be knowing the process of sampling. This is the this is a fundamental operation in signal processing. This is the process by which a continuous time signal is converted to a discrete time signal. So for example, suppose this is a signal x of t, and I am sampling this signal means I am multiplying the signal by delta functions. So basically, I am considering only those values at these sampled instances. So these instances are called sampled instances. So this is the interval between each sample. This is a sample and this is the second sample. The interval between those samples is denoted with TS. That is the time period of sampling. Okay, sampling time. And the sampling frequency, Fs, is the important parameter. Sampling frequency, Fs, is nothing but 1 by Ts, the sampling rate. Sampling frequency or sampling rate, that is 1 over Ts. Okay, so this I can denote it as x of Ts, x of 2Ts, x of 3Ts. So this is 1, 2, 3, 4, 5, 6. So maybe I have an x of nTs here. Okay, so x of nTs is nothing but x of t at t equal to nTs. So sometimes we will denote this with just as x of n, the sampled signal. Or now the continuous time signal has become a discrete time signal, right? So now the signal may look like something like this, right? So the signal will have values only at discrete instances of time, right? And each sample is in time domain, it is Ts apart, right? And yeah, so there is one important theorem that all of you may be knowing related with sampling. So from this sample signal, if I want to get back the original continuous signal, what is the minimum frequency at which I should sample this, or what is the maximum gap between two adjacent samples, right? That is precisely given by Nyquist or Shannon sampling theorem. Okay, so before getting into those details, we will try to visualize the sampling in the frequency domain. Suppose the signal x of t, okay, has a Fourier transform. X of t has a Fourier transform capital X of f. And assume that the signal is a band limited signal. Band limited means the signal has a maximum frequency beyond which the signal doesn't have any frequency component. Say it can be like this, or it can be any signal, okay, like this, or it can be in maybe like this. So lot of different possibilities are there, but the only thing is that the signal has to have a maximum frequency component. For this green signal, this is the maximum frequency component, and for the pink signal, this is the maximum frequency. The x-axis is frequency f, and the y-axis is the magnitude of x of f. Okay, for the blue signal, this is the maximum frequency component. Okay, so I'm considering only those signals that are band limited. That means the signal occupies a frequency band. It doesn't have infinite bandwidth. That is the meaning. Okay, so let us consider one signal from that. So whichever shape you are convenient with. Say I will assume that x of f has spectrum that looks like this. Frequency spectrum that looks like this, x and the magnitude of x of f. And the maximum frequency component, say it is f1. Okay, now what happens to the, or how will the frequency spectrum of the sampled signal look like? That is the question. If somebody knows, you can answer, otherwise I will explain myself. Okay, so, or if you are having any other questions, you can ask now. you can just unmute and ask, or you can just type down in the chat window, or you can raise your hand and you can ask. Okay. So, okay, this assume that this is the magnitude spectrum or the frequency spectrum of the signal x of t, which is band limited. Now, I am sampling the signal x of t and I am obtaining a signal x of nts, or sometimes I will denote it with x of n, as I told previously. Okay, because ts is a constant value. So I will use these two notations interchangeably. So I'm having x of n. Then how will the magnitude spectrum of x of n look like? First of all, what is the sampling frequency? Assume that this is fs. Okay, fs, s stands for sampling. Now, I will straight away come to the point. I'm not going into any mathematical details. So the spectrum of the sampled signal will look as follows. So this will stay there as such from 0 to f. This is f1, the maximum frequency component of the signal. Okay, and the same shape will be repeated, centered at fs, the sampling frequency, again at 2fs. Okay, again at minus fs, again at minus 2fs. So this is 0. These are the center frequencies. The remaining frequencies you can write. So the same shape, there will be a scaling in the magnitude that will be by 1 by ts that I have not written. Okay. So, but the shape will remain the same and the spectrum will repeat at every integer multiple of fs. That means 0, fs, 2fs, 3fs, it goes like that. And similarly, minus fs, minus 2fs, minus 3fs, it goes like that. So the center frequency is 0 for the original signal. Now for this sample signal, it is 0, fs, 2fs, the shape will repeat at every integer multiple of fs. Or in other words, I can write the Fourier transform of x of n, maybe x n of f. Okay, this is equal to summation k equal to minus infinity to infinity x of f minus nfs, and there will be a scaling by a factor 1 by ts or fs. 1 by ts is nothing but fs, right? So forget about the scaling. In most of the questions that you are going to encounter, that scaling factor will not have much effect. Okay, but how does this frequency spectrum look like? The shape and the frequency values, that has very importance. Okay, that is very important. So I hope it is clear. Now we will write some more frequencies. This is f1, this is minus f1. Then what is this frequency value? Can somebody tell? This point I'm asking about. What is that? What is that frequency value? What is the frequency at that point? Is that fs minus f1? Correct. Yeah, a lot of people had answered fs minus f1. Similarly, this is fs plus f1. Here it is 2fs minus f1. So here it is 2fs plus f1, and it goes like that. In the same way, it will come in the negative axis as well. Okay. So yeah, now you can see. Okay. Yeah, Govinath. So to answer that question, we need to go actually into a lot of mathematical derivations. So I can simply tell you that the thing is this. Here sampling means I'm having a signal x of t, and the sampling can be visualized as multiplying x of t with a train of impulses, right? So I'm having an impulse here, 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 and it goes like that, right? So this sampling operation can be visualized, or mathematically it can be expressed as the product of the signal x of t with a train of impulses or a sequence of impulses, right? So in the frequency domain, this multiplication will become what? Convolution, right? So multiplication in time domain corresponds to, or it is equivalent to doing convolution, equivalent to take convolution or convoluting the Fourier transform of x of t and the Fourier transform of the train of impulses, right? So what I'm saying is that multiplication in time domain corresponds to convolution of the frequency spectra of those two signals. One signal is x of t and the other signal is the train of impulses. And x of t will have some spectrum. This is one example, what I have drawn here. And the Fourier transform of the train of impulses is again train of impulses. That you can do mathematically and you can convince that, okay? That takes some time and effort to show that. And convoluting this signal with train of impulses means convoluting a signal with impulse means the shape will be shifted to that particular impulse. So there will be infinite impulses. If you convolute, if you convolute Fourier transform of impulse train with the spectrum of messaging, you will get repetition as Sarah has shown. Okay, yeah, that is precisely what I was trying to explain. So again, convoluting with train of impulses means repeating the same shape at centered at integer multiples of fs. Okay, so basically this train of impulses in the Fourier domain, in the frequency domain, will look like this: 0 fs, 2 fs, minus fs. It is again infinite impulses will be there, minus 2 fs. It goes like that. I'm not writing the scaling value. Okay, so convoluting these two will give you this. Okay, so now I'm got this frequency spectrum of the sample signal. So far so good, but there are some problems. So now I'm coming to the sampling theorem. Okay, the Nyquist-Shannon sampling theorem. Here you can see that here fs minus f1, the left side of this second or this particular shape is well greater than f1, right? Fs minus f1 is greater than f1, correct? There is no overlap between these two spectra, correct? What if fs minus f1 is less than f1? That means, say I'm considering only the first two now. This will look like this. Okay, 0 f1 minus f1, and the second shape will come like this, right? So here I have fs minus f1, here I have fs, here I have fs plus f1, right? But there is some problem here, correct? So here the frequency components will get added up. Now you will get something like this. Sorry. Here I have 0. So this will look something like this. Up to this, everything will be fine. Okay. After that, this will again increase. These two will get added up, right? Now the shape will become something like this. So this is called aliasing. From this signal, so when there is no overlap, here you can see, if I use an ideal low pass filter, say the filter look like this. Suppose this is the filter. Then if I pass the sample signal through this filter, you can see that only this spectrum will remain. Okay, what does a filter do? That will annihilate all the frequency components that are not in the pass band. So this is the pass band. That means the output of the filter will contain only these frequency components, right? I hope all of you know the principle of filtering. That means only this portion means this is same as these two are same, right? If I filter this signal that has the filter has a frequency pass band like this, then this will look like exactly like x of f, right? Now there is no repetition. I have annihilated, or I have thrown away all the other these triangles. Correct? That means I have gotten back the actual signal, right? Correct? But now in this case, if there is aliasing, you cannot get back the original signal. Correct? So there are a lot of other questions that you will be having. So about the existence of ideal filters, but now you see everything only in a mathematical point of view. Okay, so we are living in a you assume that we are living in an ideal world, and there are ideal filters available. Okay, in that case, you can get back the original signal if we are sampling like this. I hope all of you are convinced, right? But in this case, there is no way you can get the actual signal back because the signal has destroyed in the frequency domain. That means now you cannot get back the original signal in the time domain. Everyone are in the same page? Can I go ahead? Any questions? If not, we will see the question right away. Okay. Now I will, what will I do? Can I erase these things? Yeah, I will erase. Okay. Or no need to erase. You read the question once, I will read again. So one signal is given x of t, which is equal to cos 10 pi t plus cos 30 pi t. So what is the frequency of cos 10 pi t? That is nothing but 5 hertz, right? So 10 pi t means 2 pi into frequency, maybe f dash f2 or something, f into t. So here you can see the frequency of the cosine signal f to be equal to 5 hertz. Similarly, the frequency of this signal is 15 hertz, right? And the signal is this cos 10 pi t plus cos 30 pi t, and I'm sampling that signal at 20 hertz. And I'm trying to reconstruct that signal using an ideal low pass filter with cutoff frequency, again 20 hertz. Okay. And it is asked to find out the frequencies present in the reconstructed signal. So is the question clear to everyone? So the signal is this: x of t equal to cos 10 pi t plus cos 30 pi t, right? So how does the spectrum of this signal look like? Suppose I have a signal cos 2 pi f1t, x of t, not x of t, say y of t. Okay, then the Fourier transform of y of t, y of f equal to half into del of f minus f1 plus del of f plus f1. So this is the Fourier transform that you can verify. How will we obtain that? I think I have told this in the last class. Y of t equal to cos 2 pi f1t can be written as e raised to j 2 pi f1t plus e raised to minus j 2 pi f1t divided by 2. So now it is very easy to compute the Fourier transform, right? So the Fourier transform will look like this. You can, if you are having some doubts, you can ask. Otherwise, I will go ahead. So what does this mean? The shape will look like this. So this is 0, this is f, this is y of f, x and y axis. So here there will be a peak, and here there will be a delta function, two delta functions, one at f1 corresponding to this delta of f minus f1, and here it is corresponding to minus f1 corresponding to this delta of f plus f1. There will be a delta function. So it has the value is half because there is a half here, right? So forget about the half again. We just need to focus on the frequency components. I'm not bothered about the magnitude as far as this question is concerned. Okay. So now the signal x of t is given as sum of two cosine signals. One is having frequency 5 hertz and the other one is having frequency 15 hertz, right? How does the spectrum look like? Magnitude of x of f. How does it look like? This will look like this, right? At 5 hertz and minus 5 hertz, there will be peaks corresponding to cos 10 pi t, and at 15 hertz and at minus 15 hertz, there are two other peaks, right? There are two other delta functions corresponding to the 15 hertz cosine component, correct? Now, what is it told in the question? I'm sampling that signal at 20 hertz and trying to reconstruct using an ideal low pass filter with cutoff frequency again 20 hertz, correct? Now I need to sample this signal at 20 hertz. What does that mean? The same shape, I am talking about the frequency spectrum of the sample signal. The same shape will be repeated, centered at 20 hertz, 2 times 20, that is 40 hertz, 60 hertz, 80 hertz, and it goes like that. Similarly, minus 20, minus 40, minus 60, minus 80, and goes up to minus infinity, right? So let us try to find that. So first this is corresponding to, first I will draw corresponding to 20 hertz, okay? So at 20 hertz, centered around 20 hertz. So here 20 hertz will come, right? So at 20 minus 5, sorry, this is minus 5. At 20 minus 5, there will be a peak, right? And similarly at 20 minus 15. So I'm repeating this shape, same shape. That means 4 delta functions centered at 20 hertz, correct? So there will be a peak at 5 hertz. Similarly, at 25, there will be a peak, and 20 plus 15. At 35, there will be a peak, right? Similarly, the same shape centered at 0, that will have a peak at 5 hertz, at 15 hertz, at minus 5 hertz, at minus 15 hertz, right? And now at minus 20, corresponding to minus 20, there will be a peak at minus 20 minus 5, that is minus 25, minus 20 minus 15, that is minus 35, and minus 20 plus 5, that is minus 15, and minus 20 plus 15, that is minus 5, right? So all these components have got added up, correct? Now, how does the final spectrum look like? So again, this will, the magnitude will get doubled, right? Other than that, the things will look exactly the same. So now I am applying a filter centered at what frequency? Again at 20 hertz. An ideal low pass filter that will have a frequency response looking like this, right? So the sampled signal reconstructed using an ideal low pass filter will have the frequency components at 5 hertz, at 15 hertz, at minus 5 hertz, at minus 15 hertz. So that means again sum of two cosine signals having frequencies 5 and 15 hertz, the same one. There will be a magnitude difference sometimes that I am not sure about. No, again, this will be half, and half plus half again will become 1. So there will be a doubling in the magnitude, but other than that, the frequency components will remain the same. That will be again sum of two cosine signals. One is having frequency 5 hertz and 15 hertz, the other one. So what is the answer to the question? So the answer to the question is the frequencies present in the reconstructed signal are 5 hertz and 15 hertz.
Excuse me, sir.
Yeah. Go
So
ahead.
right here, sir, I have a small doubt, sir.
Yeah, sure. Go ahead.
Right here, if the low pass filter has a frequency which is not 20, like for example, if it's like if it's some 100 or so,
Yeah.
then 2fs, we'll have to take into account 2fs, which is 40 hertz, and then 40 minus 15 and 40 minus 5. We should consider all that, sir.
Yeah, exactly. 40, 60, 80, 100. Yeah, up to 100 you have to consider everything. 120 you do not need to consider, because at 120 minus 5 is 115, and 120 minus 15 is 105. So that will be outside 100 hertz band. So you need to consider all these center frequencies that can give rise to frequency components within minus 100 and 100. Okay, if you're sampling at 100 hertz.
Yes,
Not
sir.
sampling, if
Sir,
you're low pass, yeah. Go ahead.
Sir, if it is reconstructed using an ideal high pass filter of frequency 20 hertz, like we'll have to exclude these particular frequency and then write all the others, sir.
Yes, sure.
Okay, sir.
That will have infinite frequency components.
Okay, sir. Thank you, sir.
Yeah, and one more thing, if you are sampling at a different frequency, say instead of 20 hertz, if you are sampling at 25 hertz, then everything will be different. If you're sampling at 25 hertz, then we do not need to consider this center frequency 20, right? Instead of that, we need to consider 25. So 25 minus 5 will come at 20, and 25 minus 15 will come at 10 hertz, right? So there will be a lot of new frequency components will get added up in that case.
Yes, sir. Done, sir.
Yeah. Hope the question is clear to everyone. If you are having some questions, you can ask now. Otherwise, I will go to a different question that is completely unrelated with this one. Okay, not related with sampling. That's what I wanted to tell. Any questions? No? Okay, good. So then we will, this is a fairly easy question. Okay, so this is again related with some basics of signals and systems. Okay, this is a question that appeared in 2015 session 1 question paper. Okay, so a waveform of a periodic signal x of t is given here. As you can see, it's periodic from maybe -2 to 1. The shape is this, and the same shape is repeated again, right? Correct. So this is a periodic signal. So the period is, as you can find out, it is this is one period, right? So this period is 3. Now we are obtaining a new signal g of t, which is defined as g of t equal to x of t minus 1 by 2. And it's asked to find out the average power of g of t. Okay. So first of all, what is a periodic signal? If x of t equal to x of t plus capital T for all t. This notation stands for all. For every t, if x of t equal to x of t plus capital T, then the signal is told to be a periodic signal. So this is a periodic signal. You can see, take some value. Some value you can take, maybe 0. 0 plus 3 has the same value, right? You can take some other value, at -4, t equal to -4. The signal has a value 3, right? -4 plus 3. What is that? -1. At -1 also signal has value 3. And capital T, this parameter capital T is known as the time period of the periodic signal. Okay. Now, what is the average power of a periodic signal? This average power is usually defined for periodic signals, and it is defined as follows: P average 1 over capital T, 1 over time period, integral over 1 time period. You can take any time period. Okay. X of t whole square dt. Magnitude of x of t whole square dt. If x of t is a real signal, if all the values are real numbers, then this magnitude is not required. X of t square is nothing but magnitude of x of t square. Both will be the same, right? Anyway, this is a real signal. The given signal is a real signal. All the only real values are given here. No complex numbers involved here. Okay. Now from x of t, we are obtaining a new signal g of t, which is equal to x of t minus 1 divided by 2. And g of t will be again a periodic signal. Can somebody tell the period of the signal? So the period of x of t is nothing but 3, and g of t, which is equal to x of t minus 1 by 2, will have a period equal to what? Can somebody quickly tell that?
6.
Correct, exactly. So g of t will have a period 6. You can convince yourself. I can write the, so let us try to focus on one particular period. Maybe for x of t, I will focus on between -2 less than or equal to t less than or equal to 1. So this from this to this one period. Okay. So in fact, you can exclude 1. Okay. -2 less than t less than or equal to 1. So I am focusing on this period because to find the average power, I just need to focus on one time period. Okay. Now, how does g of t look like? That is very simple. We need to first shift the signal by an amount 1 to the right, and you need to expand the signal by a factor 2. You can do this in a different way. You can shift first or you can scale first, right? There are two operations involved here, right? One is so g of t equal to x of t by 2 minus half. You can write like this, right? So either you can shift the signal first and you can expand the entire signal by a factor 2. Otherwise, you can first expand the signal and you can shift the signal by a factor 1. So there are two ways you can do. I will prefer to do the second way. That means I will expand the signal first and I will shift the signal to the right. Or otherwise, you can simply plug in the value. Okay, that will be very easy. So between x of t has value 0, right? Between -2 and -1, correct? And this is the signal value between -1 and 1, the line, right? The equation of the line joining 2 points. Say this joins 0, 0 and 1, -3, right? What is the equation of this line? That is fairly easy. That is nothing but x of t equal to -3t, right? If you put t equal to 0, you will get x of t equal to 0. And if you put t equal to 1, you will get x of t equal to -1. So the signal takes value -3t between -1 and 1, right? So any questions regarding this? I'm considering only one period. You can focus on any period, maybe one from 1 to 4 or from -4 to -5 to -2. There are infinite possibilities, but I'm focusing on the one at the center. Okay. So now what is g of t? So I will draw g of t that will take value what it takes value. This is t equal to 0 and g of t will have value from -3 to -1. This will have value 0, and from -1 to +3, the signal will have a shape that looks like this. Correct? So this is 3. Here the value is -3. Here the value is 3. This is one period from -3 to +3. So period is nothing but 6. So in general, I will ask you a question. If the signal, say y of t, some other signal y of t is obtained as, say, x of t divided by some real number c, okay, then what is the period of y of t? If x of t has a period 3, then as in the question, okay, then what is the period of y of t? That is nothing but 3 into c, okay. And similarly, if you say y of t equal to some y dash of t equal to x of, say, c into t, then that is essentially compressing the signal, right? That means c 3 divided by c, correct? This is the period t. This is the period of this signal, okay. Yeah, now the signal g of t has a period equal to 6, correct? Now we just need to find out this g of t equal to 0, right? When -3 less than or equal to t less than -1, correct? And it has a value. What is this value? This is nothing but, here it was -3t, right? You just need to replace t divided by t with what? t minus 1 by 2, right? Is it correct? Correct, right? So that has a value t minus 1 by 2, right? Yeah, t minus 1 by 2. So g of t equal to minus 3 into t minus 1 by 2. So this you can write as 3 by 2 into 1 minus t, right? 3 by 2 into 1 minus t when this is in between minus 1 and plus 3. Minus 1 less than or equal to t less than or equal to plus 3. Correct? Now the average power. It's very easy to find out. 1 by capital T integral over one time period, that is between minus 3 and plus 3, g of g square t into dt. Correct? So now 1 by t is nothing but 1 by 6, and from minus 3 to minus 1, g of t is 0. So this integral will go from minus 1 to plus 3, g square. 3 by 2 the whole square is 9 by 4 into 1 minus t the whole square dt. Correct? So 9 and 6 you will get 3, 2. So this is nothing but 3 over 8 integral minus 1 to 3 1 minus t whole square dt, which is equal to 3 by 8 into 1 minus t whole cube divided by minus 1, the integral of 1 by t whole square, right? Integrating from minus 1 to plus 3. So you can just plug in now 3 by 8 into 1 minus 3. First you need to substitute the upper limit. 1 minus 3 is nothing but minus 2. Minus 2 cube is minus 8. Minus 8 divided by minus 1 is 8. Minus. Now substitute minus 1. 1 minus minus 1 is 2. 2 cube is 8. 8 divided by minus 1 is minus 8. So 8 minus minus 8. That is 8 plus 8. So this is equal to 3 into 16 divided by 8 is 2. So the average power of the signal is 6. Any questions? So this is fairly some computational question. Nothing fancy about this question. Okay. Any questions? So we have around 20 more minutes. So I will try to do 2 more questions. Those are again fairly computational questions. So this is the way I will proceed even in the coming weeks. I will take one question that needs some more explanation and some questions that just need some definitions, just like this average power and all. Okay. Or maybe 2 questions that need some involvement, just like the previous sampling question. Okay, any questions? I guess. Yeah, go ahead.
Shifting and scaling changes the power and energy, sir, or how it changes energy and power? Shifting
Actually, in fact, it doesn't change. You just need to compute the power of x of t itself. The power of g of t will be same as the power of x of t. That you can, if you want, I can do now itself. Maybe x of t has value I have written here, right? The t is in this case 3, right? For x of t, I'm talking about x of t. So x of t equal to 0 from minus 2 to minus 1, right? Minus 2 to minus 1. Minus 3t from minus 1 less than or equal to t less than or equal to 1. So now the average power equal to 1 by 3, right? From minus 2 to minus 1, the value is 0. From minus 1 to 1, 3t the whole square is 9t square dt. So 1 by 3 into 9t cube by 3, right? From minus 1 to 1. So this everything will get cancelled out. So this is nothing but something wrong has happened. Now this is 2, right? Okay, there is some problem. The shifting will not change anything, but scaling will affect the
yes, sir.
The scaling will affect. Sorry. The scaling will affect basically from whatever factor is coming here. So that is a mistake from my part. So whatever is coming here, okay, so that by that amount, say if it is becoming y of t equal to some c times x of t, so you can forget about the shifting. Then the power will come down by a factor 1 by c. So here it is 2, right? 1 by 2, right? So it will increase by a factor 2. Correct?
Yes, sir.
Yeah. Sorry for that. Uh,
So
so,
shifting will
yeah.
not the energy and power.
No, shifting will not,
Yeah.
because we are considering one particular time period, right? If you consider this time period from maybe from minus or from 1 to 4, you can do the same thing, but the thing is that this equation will get complicated, slightly more complicated. So you just need to take into account of that. But at the end, because the shape is looking the same, right? And what we are doing is that we are taking the square of that. So the square will have a different shape. Maybe if I do this here, so the shape, the triangular part will have some shape like this, and again minus part will come like this, right? So I'm seeing this area, correct? So integrating that means I am finding the area under that, correct? So if you square here, that will again remain the same because the signal value is not changing. That is again between 0 or minus 3 and plus 3, right?
Yes, sir.
So the square, we are essentially finding the area under the square of one time period, signal at one time period.
Understood, sir.
Yeah.
Thank
Okay. Okay, now I have two questions. So which one I go first? Yeah, I will go for this first. Okay. Yeah. So this is a fairly straightforward question. For an all-pass system, h of z, which is equal to z inverse minus b whole divided by 1 minus a z inverse. Okay. Where modulus of h of e power minus j omega equal to 1 for all omega. If real part of a not equal to 0 and imaginary part of a not equal to 0, then what is the value of b? Whether b equals a or a star or 1 by a star or 1 by a. So this is the question. So first of all, what is an all pass filter? All pass filter is nothing but it gives the same gain for every frequency component. That is precisely what is written here. Essentially, it can be h of e power minus j omega equal to some constant for all omega. That is the definition of all pass system. But here it is told that it is equal to 1. That means no gain or no attenuation for any frequency component. For every omega, the magnitude of the system response is 1. Okay, you may think why such a filter is needed, right? That may be for some phase correction. It has the property that it has a magnitude which is equal to 1 for all omega, but it will have a phase component. Okay, so you might have heard of linear phase filters and all, right? So for if I use non-linear filters, in order to correct that phase, we can use these all pass systems. So that is the typical use of these systems. Okay, so now coming back to the question, it is given that h of z, which is nothing but the transfer function, equal to z inverse minus b divided by 1 minus a z inverse. So from that, we need to find the frequency response. From the transfer function, how can we find the frequency response? Frequency response is h of e power minus j omega or h of e power j omega, which can be obtained by substituting z equal to e power minus j omega, right? So h of e power j omega equal to, so we just need to substitute z equal to e power minus j omega. So z inverse will become e power j omega minus b divided by 1 minus a e power j omega, correct? And it is told that the magnitude of h of e power j omega equal to 1. Or I can square in both the sides, right? The magnitude square of h of e power j omega equal to 1 for all omega. So now how can we find this? This is nothing but h of e power, so 1 equal to h of e power minus j omega whole square which is equal to h of e power minus j omega into h star of e power minus j omega. Correct? That is the complex conjugate of h star. So that is nothing but e power j omega. So h of e power minus j omega is here, e power j omega minus b divided by 1 minus a e power j omega into h star. That means e power j omega minus b whole divided by 1 minus a e power j omega whole conjugate. Correct? So the conjugate of a fraction a by b or not a by b, a and b are here in the question. So I will take something else. X by y whole conjugate is nothing but x conjugate divided by y conjugate. Similarly, x plus y whole conjugate is nothing but x conjugate plus y conjugate. So star is not the proper notation. Usually we use a bar, but I will stick with star. Okay, e power j omega minus b divided by 1 minus a e power j omega into the conjugate of e power j omega is nothing but e power minus j omega. Conjugate of b is b star. The conjugate of 1 is nothing but 1. 1 minus conjugate of a is a star and e power minus j omega. Correct? So now we can just multiply this brute force multiplication. E power j omega into e power minus j omega is 1. B e power minus j omega minus b star e power j omega. Correct? Plus or minus b into minus b star, that is nothing but plus magnitude of b whole square. And the next one is 1 into 1 is 1 minus a e power j omega or minus a star e power minus j omega plus magnitude of a square. Correct? Because minus a into e power j omega into minus a star into e power minus j omega is modulus of a square. E power j omega and e power minus j omega will get cancelled out. Correct? Now, by simply observing the numerator and denominator, what do you think? B equal to from these four options? A star, 1 by a star or 1 by a. Basically, the coefficient of e power minus j omega should be the same and the coefficient of e power j omega should be the same, both in the numerator and denominator, because this is equal to 1, right? We have started from here. This is equal to 1. This must be equal to 1. That means both the numerator and denominator should be the same. Correct? So B equal to what? A star, right? So focus on these two terms. You can correct? So the coefficient of e power minus j omega is B and a star in the numerator and in the denominator, correct? Here also you can see. So basically, if B equal to a star, this magnitude square of B square and a square, magnitude of B square and magnitude of a square will be the same when B equal to a star, and 1 is the same in both the cases. And in order to become this equal to 1, this fraction equal to 1, B must be equal to a star. Any questions? So the answer to the question is option B, a star. Any questions?
So last step, can you explain again, sir? Last step.
Yeah, sure. So up to this, everything is fine, right? So this must be equal to 1, correct?
Yes, sir.
So there are multiple ways. The easy way is, how can this be equal to 1? Anyway, the magnitude of B square and magnitude of A square must be the same, right? Now you just need to compare the coefficient of e power minus j omega or e power j omega. Both will give the same. One will give you B equal to A star and the other one will give you B star equal to A. That means B equal to A star. These two are the same, right?
Yes, sir.
So you just need to see that. Otherwise, what you can do is that you can plug in for every B, you can substitute A and you can see whether these are same or not from the first look itself. And it is told that A is purely a complex number. The real part is not 0 and imaginary part is not 0. It's a complex number itself, not purely imaginary, neither purely real. Okay.
Yes, sir.
So you can substitute everything and you can see that's the other way, but just looking at this, you can say B equal to A star, right? Why do you need to
Sir, can you
go for
please scroll up once, sir?
Yeah, sure, sure.
Yes, sir. Thank you, sir.
Yeah, suppose if A is say purely imaginary or purely complex, not purely complex, purely real, you can say B equal to A and all. That's why they have specifically told this. Okay. If A is a real number is a subset of complex numbers, right? So if you consider in that way, you will get some other options as the answer. But in order to avoid that, they have specifically given this real part of A not equal to 0 and imaginary part of A not equal to 0. Okay, so I have one last question. I think I can finish that maybe within 5 to 10 minutes. Okay, or somebody asked something in the chat box. Yeah, I'm recording this session. So I will upload this in some drive and I will try to share that maybe in the NPTEL portal where you are joining in this meeting. There itself, the link may appear maybe within 2 or 3 weeks. Okay. So I have recorded the previous session as well. This session will also come along with that. Okay. Yeah. Yeah. Now this is the question. I think all of you are able to see this. A filter structure is given here. So y of n can be written as, here x of n is coming directly, correct? X of n is coming directly here with the gain 5, right? 5 times x of n. So here after 2 delays with a gain 5 with a minus sign, it is coming here. That means 5 times x of n minus 2, correct? It's clear, right? This is the only part in this question. Other than that, everything you can simply do. If you understood this, I can go ahead. So from this, you can find the unit sample response. Unit sample means the discrete equivalent of delta function. That means the signal delta n will have a value 1 at n equal to 0. And the signal will take value 0 at all the other points. So from that, if the input of the system is delta function or the unit sample function, we will get the impulse response or the unit sample response of the system. So that will be typically denoted with h of n. That is nothing but 5 times delta of n minus 5 times delta of n minus 2, right? I just need to substitute x of n, the input signal, to be the unit sample signal. So h of n equal to 5 times delta n minus 5 times delta n minus 2, correct? So from this, we can find the transfer function h of z. That is nothing but the z transform of h of n. That 5, that means z transform of delta n is nothing but 1. So 5 into 1 is 5 minus z transform of delta n minus 2 is z power minus 2. So this is 5 z power minus 2. So from this, as in the previous question, we can find the frequency response h of e power j omega by substituting z equal to e power j omega. 5 minus 5 e power minus 2 j omega. Correct? Now, in order to find out whether the filter is a low pass filter, high pass filter, or band pass filter, or a band stop filter, you can do the following step. Okay, I will explain that. Usually, not usually, a low pass signal will have a frequency response like this, right? So in the discrete domain, we need to consider the frequencies between minus pi, we need to consider the frequency components between minus pi and pi, correct? So the discrete frequency will be between minus pi and pi. That's a periodic signal actually. So the same shape will be repeated like this, because I have told earlier, right? When you are sampling a signal, correct, the frequency spectra will repeat, right? So here, this is between minus pi and pi, the discrete frequencies. When the unit sample response has real coefficients, just like this, okay, just like here it is 5 and minus 5, right? In that case, the frequency response will be symmetric about the y-axis. So you need to consider only the frequency region between 0 and pi, correct? So this is omega, and this is h of e power j omega. So this is in fact the angular frequency, not the discrete frequency. That will be between minus 1 and 1. And this will be between minus pi and pi. So here, yeah. So a low pass filter, how does it look like? This is not pi. Pi will be somewhere here, right? So the low pass filter means the filter will allow to pass the low frequency components, and this will annihilate the high frequency components, correct? Or maybe this, if it is, this will look like this. So at omega equal to pi, h of e power j omega, the magnitude, will be equal to 0. Not only the magnitude, h of e power j omega itself will be 0 at omega equal to pi for a low pass signal. Low pass. And at omega equal to 0, h of e power j omega will be not equal to 0. That is also very important. Now let us see a high pass filter. So the high pass filter characteristic will look like this. This will look like this. High pass. At omega equal to 0 or at omega equal to pi, h of e power j omega not equal to 0. That means that will give a non-zero gain for the signal that is passing through at omega equal to pi, the frequency components omega equal to pi. Okay. At omega equal to 0, h of e power j omega will be equal to 0. So here you can see at omega equal to 0, h of e power j omega is 0. Now, two other things. One is a band pass filter. So band pass filter, it's very interesting. It has value h of e power j omega equal to 0 at omega equal to pi and at omega equal to 0. At both these frequencies, correct, the frequency response will have a 0. Now coming to the band stopped filter, correct, this will have some response looking like this. So this is band stop or band reject. So at omega equal to pi and at omega equal to 0, h of e power j omega is not equal to 0. Is it clear? So from the obtained frequency response, we need to substitute omega equal to 0 and omega equal to pi, and we need to see whether the values are 0 or non-zero. Corresponding to that, we can get the nature of the filter. So h of e power j omega is 5 minus 5 e power, what is that? 2j omega, correct? So first we will find out h of e power j omega at omega equal to 0. That means 5 minus 5 e power 0 is nothing but 1, right? So this is equal to 0. What does this mean? Now, can it be a band stop filter? No, correct? Can it be a high pass filter? Yes, it can be a high pass filter. Can it be a low pass filter? It cannot be, right? H of e power j omega must be equal to 0. Must not be equal to 0. Sorry. H of e power j omega should not be equal to 0 at omega equal to 0, right? For a low pass filter. But we have got that h of e power j omega equal to 0 at omega equal to 0, correct? So it can neither be band stop nor be low pass. Now we need to see whether it is a high pass filter or a band pass filter. How can we see that? We need to substitute h of e power j omega where omega equal to pi, correct? H of e power j omega equal to pi. If it is equal to 0, then this will be a band pass filter. If it is not equal to 0, the filter will be a high pass filter, right? So now it is equal to 5 minus 5 e power minus 2j omega equal to pi. So 5 minus e power minus j 2 pi is nothing but 1 again, right? So e power jx equal to cos x plus j sin x. So Euler's formula that everybody must be knowing, right? So this is equal to 0. So what does this mean? So is the filter a high pass filter or a band pass filter? Can somebody tell?
High pass filters.
Huh? High pass or band pass? We got omega equal to h of e power j omega equal to 0, both at omega equal to 0 and omega equal to pi.
It's a band pass. Sorry.
It's a band pass filter. So the answer to the question is the given filter is a band pass filter. Okay. So it's already 7:05. We are already run out of time. So if you are having any questions, you can raise now. Otherwise, we will wind up the session. And in the next session, we will be discussing some questions related with linear algebra. And after that, we will discuss some questions related with communication systems. Some of you have already shared some questions related with these areas. If you are having some questions, you can mail me at this mail ID, krishnan@iaac.ac.in. Questions related with communication systems, signals and systems, or with probability theory or linear algebra. If you are having some specific questions, you can share me. Okay. In the next session, I will be dealing some questions related with linear algebra or specifically focusing on matrix related questions, matrices. Okay. If you are having some questions, you can send me.